This program is sponsored in part by the Elizabethtown College Summer Scholarship, Creative Arts, and Research Projects. Elizabethtown College. Educate for service.
And the real story, the point of view that I want to discuss today, is that in fact it doesn't make any sense because it's wrong.
The belief that objects possess properties, whether or not we choose to measure them, is called realism. And Smolin's claim is that quantum mechanics is wrong because quantum mechanics doesn't provide the values of unmeasured properties. This is called no counterfactual definiteness, and it can arise for entangled quantum systems, just as the mysteries of delayed choice and quantum erasure introduced in the previous episode. No counterfactual definiteness is the topic of this episode. The example of no counterfactual definiteness that I will use is from, you guessed it, David Mermin. This was the paper I read in 1994 that introduced me to the mystery of quantum mechanics and motivated my research into foundations of physics. I had taken 9 undergrad and grad courses in quantum mechanics en route to my PhD in physics, but terms like Bell's inequality, the Einstein-Podolsky-Rosen paradox, the measurement problem, and delayed choice were never mentioned. As I stated in the last episode, there are plenty of problems in quantum mechanics to solve that do not involve mysteries, and when I was a student until 1987, foundational problems were just not included. Indeed, you still won't find those issues mentioned in many textbooks on quantum mechanics or modern physics. So I'm very thankful that Mermin took it upon himself to educate physicists like me about the mysteries of quantum mechanics. And while he subsequently published even more accessible examples of such mysteries, I'm going to explain this one because it includes an introduction to Bell's inequality and it reveals a direct connection to the relativity of simultaneity and special relativity. Yes, that would be no preferred reference frame. Here is how the Mermin device works.
This is the Mermin device. We have a source of our 2 particles. Come out this way, that way, to our 2 detectors, which can be set in settings 1, 2, or 3 by Alice and Bob. And there are 2 possible outcomes with the indicator lights on top for each trial. And let's run a trial. Okay, in this trial, Alice had setting 2 and got a red outcome, and Bob had setting 2 and got a green outcome. Next trial, Alice kept hers at setting 2 and now gets a green outcome. Bob kept his at setting 2 and now got a red outcome. And now we have fact 1 about the Mermin device. In all trials where we have the same settings, we have to get different outcomes, either green-red or red-green. And they're split between the 2 possibilities, 50-50. Now we can choose other settings. Here we see Alice has chosen setting 3, and Bob has chosen setting 1. Alice got a red outcome, Bob got a green outcome. Here we see Alice kept setting 3, Bob has kept setting 1. And they both got red outcomes. And here's fact 2 about the Mermin device. Overall, all the trials, same settings and different settings. Half the time you get different outcomes, green-red or red-green, and half the time you get the same outcomes, red-red or green-green. Those are the 2 facts about the Mermin device that we need to explain.
Mermin uses the outcomes of his device to introduce the quantum mystery of no counterfactual definiteness, or no realism, to the general reader. He then challenges the physicist reader to explain to the general reader how it, the Mermin device, produces its outcomes. To date, 38 years later, no one has successfully addressed his challenge to everyone's satisfaction. Here is what the device does. The physical instantiation of the Mermin device that I'm going to use concerns the entanglement of the property of spin. Here we see spin evidenced in a beam of silver atoms passing through our Stern-Gerlach magnets, and they are deflected up or down relative to the north or the south poles of the Stern-Gerlach magnet.
That's our binary outcome corresponding to the red-green outcomes in the Mermin device. We have a pair of such particles. Here's our source corresponding to this element of our Mermin device. We have our Stern-Gerlach magnets for each of Alice and Bob corresponding to our detector devices. We have 3 possible orientations for our Stern-Gerlach magnets corresponding to the numbers 1, 2, and 3 on each of the measurement devices. And then, of course, we have our binary outcomes on our detectors for Alice and Bob corresponding to the indicator lights red or green on the Mermin device.
Concerning his device, Mermin wrote, "Although this device has not been built, there is no reason in principle why it could not be, and probably no insurmountable practical difficulties. Sure enough, the experimental confirmation of the violation of Bell's inequality per quantum entanglement can now be carried out in the undergraduate physics laboratory. Entangled photons, non-locality, and Bell inequalities in the undergraduate laboratory, American Journal of Physics, 2002. Thus, there is no disputing the conundrum of the Mermin device has been experimentally well verified and indicating its prediction by quantum mechanics."
So, what's so mysterious about fact 1 and fact 2 concerning the Mermin device? Okay, well, fact 1 said, whenever Alice and Bob choose the same measurement setting, they have to get different outcomes. How can that be? When the particles leave the source, they have no idea what those settings are going to be. Indeed, these settings can be switching. In experiments, they're typically switched megahertz frequencies. There's no way the particles can know how they're going to be checked. So Mermin says, hey, it must be the case that they're prepared for all possible measurements, right? Suppose, for example, that Alice's particle will be red in setting 1. Then that tells us that Bob's particle has to be green in 1. If Alice's particle is going to be red in 2, Bob's particle is going to have to be green in 2. And if Alice's particle is going to be green in 3, Bob's particle is going to have to be red in 3. Okay? These are called instruction sets to account for fact 1, to guarantee fact 1. Now, there are only 2 types of instruction sets that are possible. The one I just showed you here, where you have 2 of one color and 1 of another. Or they're all reds and all greens, or all greens and all reds. So let's look at what happens in the cases where, for example, we have 2 of one color and 1 of another color for Alice and Bob's particles instruction sets. Well, we're going to get disagreement. 1, 1, 2, 2, and 3, 3. Right? That's the way it was designed, obviously. But we also will get disagreement here, see, for 1, 2, and 2, 1. Getting a little bit messy there. All right, so to recap, we have disagreement for our red, red, green for Alice and green, green, red for Bob. And in 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1. That's 5 of the 9 possible measurement configurations. In the other 4, 1, 3, 3, 1, right, 2, 3, and 3, 2, you're going to get the same outcomes. So overall, in 5/9 of the trials, you're going to get different outcomes whenever you have instruction sets like this, 2 of one color and 1 of another. The only other possible way of doing it, again, is all of one color, all reds and all greens, vice versa. And in those cases, in all those trials, it's 100%, right? 9/9, you're going to get opposite outcomes. Therefore, overall, it has to be the case, if you have these instruction sets, that you have disagreement in more than 5/9 of the trials. And that is your Bell inequality. And that is exactly what the quantum situation violates, because in the quantum situation, it predicts you're only going to get different outcomes in half the trials. And so that's the mystery. How do you account for fact 1 and fact 2 without using instruction sets? Because instruction sets don't work.
What is the nature of physical reality? How does the device work, such that both fact 1 and fact 2 obtain according to quantum mechanics? And where does no preferred reference frame come into play? These are the questions I will answer in the next episode. As with delayed choice in Quantum Eraser, we will need to rise to Wilczek's challenge and look beyond the dynamical universe.